That is fine, yes. Okay. Hi, everybody. I'm really grateful to the organizers to give me this opportunity to congratulate today, to give a talk and to congratulate Joe, to whom I have a huge respect, and also, of course, to his work. And I tried to find some pictures on the internet, but I found this one, which is used here at the conference front page, the best one. And there, probably, Joe has a very modest presence on the internet. I found only 3 or 4 pictures. So in general, he is a modest person, in spite of the fact that talking to him is a pleasure always, and it's very inspiring. And I found only this picture from the last IGST, Integrability, Engage and String Theory meeting, which is the 21st meeting. And you see he's here. Okay, Ivan Kostov is not dancing. He just tries to keep low to that everybody would be seen. Okay, and actually, speaking about IGST meetings, it's to a great extent thanks to Joe, to his participations, to his talks, to his works, that this conference and in general this subject is alive and doing relatively well. Yes, and he's one of the pillars of our subject of integrability, engage and string theory, and hope it will go on like that. Actually, on these IGST meetings, there is a tradition from many years ago that on the conference dinner, the youngest and the oldest participant give a little speech. So very soon, Joe, this will be your turn. But not so far. Yeah. Okay, so I mean, usually we have very short encounters with Joe on some conferences. Typically, I'm walking to the hotel from conference hall or from conference hall to the hotel, and he's jogging by. Yeah, but many conversations I remember, and I remember very curious conversations, not even scientific. I will speak later about it, but even about politics. Like a few months ago, Joe tried to convince me that to have a president slightly senile for a country is not necessarily a bad thing. And I was surprised. It was bizarre to me, but thinking a bit more a few months ago and observing our world, I decided maybe he was not so wrong. And so we have only one common paper, but this is an important paper, one of the milestones of our subject, the so-called KMMZ paper about the finite gap solutions in string theory on ADS 5 times S5. And I had an opportunity to witness Joe's insight, power of insight, and also technical, the excellence of what he was doing there. It was we never met probably before, and even this paper was done sort of on the internet. But then, of course, during at least the AGST meetings, we met many times. Hope you consider me as your friend. Yeah, okay, now I don't know many jokes. I don't have so many jokes as your students and people who know you better, so let's be serious and let me now speak about this subject. So it's about studying the so-called huge operators in Kazakov 4 super young meals. And in this audience, I shouldn't even pronounce these words. Everybody knows what is super young meals and what we are after. Usually we study operators, which are in general functions of various traces of words. So for local operators, for example, words build of the fields of the theory, and the first interesting set of quantities is of course the anomalous dimensions. Then we have structure constants, which are related to 3-point correlators, and so on and so on, the usual lore. Now, what kind of operators should we learn, should we study in this theory? So these are three kinds, at least at large unlimit, which is the usual limit, the most interesting limit in this theory, the richest one. So we can study little operators, like single trace operators, which are directly related to this ADS CFT, strings on ADS5 times S5. And here we have integrability, which was started by Minahan and Zarembo, by their one-loop calculation. Probably I should mention also Ben Royban Polchinski paper. I forgot to put it here. Then our KMMZ was probably another milestone, etc., etc. And then so far it ended up with quantum spectral curve. We had a nice talk of Simon today. But let's now go further in dimensions, in the size of dimension. There are also operators which we call giant, when the dimensions of the order n. It's still ADS, it's still very excited string on ADS. A good example is giant gravitons, which I will mention later. And there are huge operators where the dimension is of the order of n squared, the same as the action. So they really change completely the background. And it's not at the ADS anymore. And here we search for black hole states, etc., etc. In general, they are very difficult to study, of course. There are probably no integrability so far observed, but there exists, fortunately, a set of BPS operators, like 1/4, up to 1/16 BPS, which are protected, coupling independent. And their dimensions are integers of half integers, and they're dual to interesting geometries. The most studied one is the so-called LLM geometry of Lindlunin-Maldacena. And sometimes it can be studied by matrix models. It can be always mapped, this kind of state, correlators of these states on matrix models, and some of these models, not all of them, can be solvable. I think there is an echo. Yes? No? It's only for me, maybe. I see. No problem. Okay. So what kind of 1/2 BPS operators we can study? They're all functions, invariant functions of chiral scalar field, which is y times 6 vector of field phi, where y is the null vector. And the best studied set of such operators are character type operators. They are characters in representation R of JLN of this scalar field. And then there is another interesting set, so-called coherent state operators. I will speak at the end of the talk about them in relation to 1/4 and 1/8. These are not much different from characters. They also depend on one in a different way, not like characters, but also on the invariance of this field. And also another interesting set, maybe not very well studied, although there have been some papers on it, like Velasquez. We call it exponential operators. They are just exponent of trace of some function of usually polynomial of field Z. Z is just this field y times phi of x. We call it Z here. And these operators, I mean, their two-point functions or just their renormalization properties can be described by this LLM metric, which is given here with this symmetry, two S3 spheres, one from R symmetry, another from Minkowskian. And there is a function zeta entering everywhere in this metric, which can be computed knowing only one function, the density rho of z bar z, a two-dimensional function which actually takes the values of plus minus 1/2, and here at least. And so this scalar factor and the vector potential can be expressed through rho. Knowing rho, we can restore this metric always. And by these formulas, which are kind of Biot-Savart formulas in electrostatics. Then there is this picture that on this z-plane, the black spot is when rho is +1, everything white is -1, and when it is black, one sphere blows up, and when it is white, another blows up. Then all this is called bubbling geometry in the literature due to this kind of picture. Okay, and then we know exactly for these operators what is the shape of this black spot. Say for operators, they are concentric circles, which is from original LLM paper. Then for these operators, we have arbitrary shape of the spot. We can play with the couplings of potential or with the parameter lambda, which is a diagonal matrix, by essentially changing it in any way. And in this way, you can have virtually any possible LLM background. Okay, then we want to study the correlation functions of these operators. So character operators represent the full orthonormal system of 1/2 BPS primaries, and they're easily calculable if you normalize it by 1, which can be always done. You have just this standard factor, the standard conformal factor, where y's are products of these 6 null vector, 6 vectors, null vectors, and this typical xi minus xj in the power. Actually, I guess here 2 should be either here or there, it should be present. Okay, and where L is essentially the size of Young tableau of this representation. Then you can also compute 3-point functions in this way. You have again a standard factor, which typically arises in Polyakov form of 3-point function in the conformal theory, and also, but you have already a factor which is universal, which really after all normalizations, describes the structure constants, depending on three different representations for three operators. And the computation in 1/2 BPS story, the computation of this factor is purely combinatorial. Roughly, you take three such operators representing various products of traces, etc., and you connect them with all possible propagators. The space dependence and Y dependence of propagators is pulled out, and essentially you compute only the weak contractions of these fields. And it's a purely combinatorial problem, which can be studied with an interesting matrix integral. We studied it recently, a year ago or so, with Harish Murali. And by the way, I forgot to mention my co-authors in this paper. They were on the front page. And the paper is out today. It's Prokopy Anempodistov, my student, and Harish Murali, the student of Pedro Vieira, and Adolfo Holgin, a postdoc from Trinity in Dublin. Okay, and we found, for example, a nice eigenvalue representation for a single set of eigenvalues with these interesting objects, determinants of Hermite polynomials, and this can be studied since it's a saddle point calculation. The object can be studied. Essentially, it leads to some solvables, 1+1 dimensional hydrodynamics, Burger's equations, etc. But I want to speak about a different point of view on this, on the calculation of these correlators today. Namely, I will, according to our this new paper, it will be calculation using the complex matrices, which is, you'll see why it's useful, this point of view on the subject. So in general, we study if our operators are BPS and if the correlators are protected, which is not always the case, of course. We drop the coupling dependence. It's just Gaussian part of the scalar Gaussian part of the action. We study scalar operators, which remains from super Young-Mills. And in complex matrices, essentially you compute this kind of Gaussian integral with but with insertions. And the one-point function will look as follows: just integral over complex matrices, and the three-point function already is some calculation to do. So if we have, for example, operator with its complex conjugate like here, and we insert arbitrary probe, also BPS, we can always rotate the field, generically rotate the field of the probe to Z plus Z bar. When here you have Z and Z bar, it's essentially a very generic representation, and just a symmetry of the object is used. And this F probe is related to the original probe, depending on this function, in this Gaussian way. So you have to do this Gaussian transformation, which we call Q transformation. So, but essentially, this is the problem. And what is the advantage of complex matrices? The advantage is because once you, for example, in two-point function, you compute the shape of eigenvalue representation of these matrices, it's exactly the shape of droplet in LLM metric. So you have direct ADS, that's a gauge gravity correspondence then for these operators. Okay, so this is kind of a new formula which we use to study three-point functions. After some work diagonalizing, or rather taking sure decomposition of these matrices, in two-point function we arrive at very familiar form in terms of eigenvalues, say in normal matrix model it's the same, which has a long story in various subjects. For example, in Laplacian growth problem, there are many papers on it. Essentially, when you study the saddle point equation, you can present it this way. I forgot. This way. This Vandermonde modulo squared operator, essentially, since it's a bunch of logarithms in effective factors, you can represent it as inverse Laplacian. So this is the saddle point equation. If you act by Laplacian on both sides, you obtain rho. You kill, due to holomorphicity, both v's, and v and v bar, and this gives just 1. So you have essentially rho up to some shift, maybe 1/2 minus 1/2, it's just a matter of shift. You get that rho is 1 in some domain which is defined by potentials, and 0 outside of this domain. And then there is a nice story. You can define shape of the boundary by by constructing an algebraic curve. For example, for cubic potential, this is the shape of the boundary when W changes in this way. Phi is from 0 to 2 pi. Then following phi, you get various pictures depending on the parameters of the potential. This A and B depend on T2, T4 in a calculable way, of course. And you can get various shapes. For example, the curve is very smooth when it's under some critical regime, and it can be intersecting of supercritical regime when you change parameters. But there is also a critical regime when it gets some kind of beaks, some cusps in various places. So that, for example, in this asteroid curve, particular curve, we have a cusp, and if we compute the corresponding two-point function, we will get this typical critical behavior. T is essentially the area of inside this. So all these are the shapes of spots, yes, the boundaries of the spots for various parameters. So we get this critical behavior, which is actually in the old matrix 2D matrix models for 2D gravity. It was interpreted long ago as the pure 2D gravity case. Then you can tune another coupling. There are two actually couplings here, and you can tune to what we called in the old times Ising plus 2D gravity with this kind of singularity, etc. So that a similar picture can be established for coherent state operators. I have no time to speak about it. What is interesting here, that maybe by summing up 1/n series, as we did in this non-critical string theory, we find universal regimes described by Penlever-Wahn equation, higher points by modified KdV equations, so that we study already quantum gravity. It's kind of a topological, of course, sector of quantum gravity, but still, it should say something about quantum gravity effects in 10-dimensional supergravity corresponding to n equals 4 Young-Mills. So I think it's a very interesting direction to develop. Now, we studied also, we found some more evidence for super Young-Mills gravity correspondence studying so-called huge, little operators. Little means that you have only a few fields participating in this operator, and we successfully matched it from the data on the gravity side. Namely, and the subtlety here is to get correct normalization. I wanted to say that the results belong to Skenderis and Taylor on the gravity side, and they just took the particular LLM background and expanded it into modes and picked up the modes at the boundary of where the space is ADS. They expanded around ADS, of course, and then in this way they computed a few operators, a few lowest operators. In gauge theory, they correspond essentially to this kind of operators with low dimensions and charges. These two labels means dimension and charge. So we have here 3 examples. And then here are the results of their calculation. And we essentially repeated repeated the same calculation on the Young-Mills side using our matrix model. And we perfectly reproduced all their results in a very natural normalization. So I think it's in their paper there was only a comparison of extremal operators, but here it's much bigger list and they are more representative, these operators. Okay, so we have a little bit of ADS gravity, say superior Young-Mills gravity correspondence results, and now some results which already concern these huge giant operators, like we took a giant graviton and 2 character operators, which are huge, this big Young tableau. So the giant graviton is described with this anti-symmetric representation. Symmetric we also did, but I give here the result with anti-symmetric representation of length delta. And after some manipulations, it can be brought to this nice eigenvalue problem, exactly, for any n. Here we have a Hermite polynomial, and this. So essentially, this and those factors and this factor correspond to giant graviton, and this is huge background. This integral can be computed exactly, and here is the result of exact calculation, very simple one. And in the large n limit, which is interesting for us, you get this result. So delta essentially is the parameter of giant graviton, and k. It's for rectangular Young tableau. Sorry, this is the result for representation, which is a rectangular Young tableau. So k is entering here, but one can actually do the calculation for Young tableaus of more general type, like for example from consisting from 2 or 3 rectangles, etc. So it's essentially you can find the exact results for virtually any Young tableau. And you could do also this calculation, which is instructive, by saddle point in this integral, because sigma is an integral, the single integral with factor n in front of it. And the result will be the same, but here is a nice representation of this quantity where you have this factor, and that one corresponds to giant graviton insertion, and rho is simply this spot, this droplet of huge operators. So this formula is a generalization. It's true not only for characters, but it's true for any background of these huge operators. And it looks like an instanton in matrix models. So of course, it brings us to the idea that maybe we could reproduce it in supergravity from a configuration of LLM metric plus some D-brain. Okay, then we have some explicit result. How much time do we have? Maybe 5-7 minutes. Okay. now about heavy general stuff. So as I said, there is a general method developed in our paper with Vera and Morale, but and there are some nice exactly solvable cases. For example, if we have 3 operators with triangular Young tableaus, we can bring it to this model, which already is kind of a particular case of Kostov's ON models. It was solved exactly by some algebraic curve representation. It's like n equals 1 case, like Ising case of this model. And okay, you can really restore the whole density of x's and get exact result for the corresponding structure constant, which is just a number, not very interesting, but exact. Okay, then there is another case when you have 3 operators of exponential type, and then it brings us to the 3-state Potts model, coupled to 2D gravity, which was studied for many years, starting from my paper when it was diagonalized, and then solved in a series of papers in a similar way. So I don't explain the solution, but it's very similar to this model, the singular integral equation which you have to solve, etc. The same algebraic curve with slightly different functions here. Okay, and so it's maybe the most, then the critical regime corresponds to this behavior, 11/5, which corresponds to this 3-state Potts model. The charge of the matter is 4/5. And of course, the most interesting questions here in all this subject for 1/2 BPS is to generalize these 3-point functions, to generalize the LLM metric for the calculation of 3 operators, because then now you have 3 asymptotic regimes for 3 operators, which asymptotically ADS, but of course such a metric should be much more complicated than LLM. Somehow it seems to me that still it's possible to solve this, but I'm not a specialist in finding these backgrounds. Okay, now it's very little which is left, and very little to say about 1/4 and 1/8 BPS coherent state BPS operators. These are already quite complicated matrix models. The analog of characters was proposed by, I think, Ramgoolam et al. In these papers, but they're virtually unsolvable, essentially unsolvable, these kind of matrix models. One interesting operator, 1/8 BPS, was proposed by Bernstein and Wang quite recently. It looks very simple. You integrate over unitary matrix G. This e to the trace G dagger, P mu, G x mu. And you sum up over mu's, 1 to 3. This is a sum of 3 terms, so it's not the integral of its Exon-Joubert type, only for 1/4. So if you put 1 of p's to 0, it will be 1/4 BPS. If you put 2 out of 3, it will be 1/2. Then, of course, it's Exon-Joubert. Otherwise, it's a complicated integral. I don't know how to compute it. And P is our parameters. So P are fixed parameters, which are commuting matrices things. I write it later. The parameter matrices. And probably this is the full set of 1/8 BPS operators. There are now, if we compute the pair correlator, we integrate over x mu, which are these 3 scalars. So we integrate with Gaussian measure, we get this 2-point function. Again, looks simple, but since you sum up over mu's, it's not a known integral over unitary matrix. You can do it in perturbation theory or in strong coupling when P goes to infinity, but not really, no exact results are known. And, but the gravity dual is kind of known, or at least it's proposed, but we don't know exact correspondence between parameters of these operators and parameters of the solution. It was in the papers of Donus, and then Donus with some co-authors many years ago, but at least it's a hope that this bubbling geometry for quarter or 1/8 BPS could serve for describing the large limit of this of these two-point functions. Now, one solvable case is, of course, if of about 3-point functions. Of course, it's even more complicated. But one solvable case, if we take exponential operators with. Okay, so, it's not yet solvable, because if we take arbitrary v of z, we get this function of these OP operators with two exponential operators. The parameters p commute. So this is a difficult function, complex matrix integral. But if you take Gaussian v, of course, you take Gaussian integral, you get kind of an interesting example of 3-point function where, I mean, the 2-point function would have elliptic droplet. So I think it's something to keep in mind. And now the last transparency, which is the most speculative, but for me it's the most interesting, because maybe we could approach these matrix models on a completely different ground. Namely, looking at this the 2-point function of 1/4 of 1/8 BPS operators, we notice that it exactly is exactly equal to the Yaguchi-Kawai, quenched Yaguchi-Kawai reduction, dimensional reduction of principal chiral model for 2-dimensional and 3-dimensional case, respectively. Namely, this is the principal chiral model. Just G is the unitary d-dimensional field. And the reduction goes as follows. You just impose the dependence of G on X by these diagonal matrices. So X is essentially explicit. You plug into the action, you get this expression. P is here a matrix of quench momenta, P1 up to Pn, with dimensions 1, 2, up to 3. So essentially, it becomes this, and of course, the statement of Yaguchi-Kawai was that this at the large n limit, these models coincide. The large n principal chiral model and its reduced Yaguchi-Kawai reduced version. But of course, there are many caveats. Sometimes it doesn't work because we don't find the physical phase, for example. And sometimes we do find. And it's still not clear to me whether this model describes the phase with physical asymptotically free behavior, like what Igor Klebanov wanted to stress in his talk, that we have to find some theory with asymptotically free behavior. And but maybe it is, because, for example, if you expand by perturbation theory around the unit matrix, you get the results of the standard results, one loop results, for example, you reproduce it perfectly. But there are various other vacua, like permutations of, and it's not clear whether this other vacua will disorder the asymptotically free phase. I think we have to think deeper on it. And there is a possible fix, which is also quite speculative, namely, the presence of physical phase was checked by Monte Carlo simulations in the twisted Yaguchi-Kawai reduction, where you see you have, instead of these commuting matrices, P mu here, you have gamma matrices which Q commute with some unit factor Q. And then it really works. You can check that changing lambda, you can at least have the asymptotic freedom. It was checked by Monte Carlo, etc., which is trustful. And then suppose we have the beta. Can we model this operator in super young Mills? Suppose we have the following operator in beta deformed super young Mills in Lee-Strassler deformation, which was mentioned today. Let it be this coherent state type. So instead of this P, I mean, we have P and Q here instead of this P mu's. Just a new notation. Sorry, the group here is the same, little g. I should have changed it. And then integrating it, we find this version actually of it will integrate. I mean, computing the two-point function, we discover this kind of partition function of the principal chiral model already in this physically viable twisted version. And this operator, I mean, it's a hypothesis that it is BPS, that it is protected. At one loop, it is protected. It's checked. Nothing is known in more than two loops. And there is only planar calculation of Joe and Zieg up to 4 loops in beta deformed theory, but in planar limits. If I think it's possible to lift the whole result into any n, for any n, it's important here, of course. And in that case, maybe it's enough to prove that this is a protected operator. So it's an open problem. But if it's protected, for sure, we have principal chiral model as a BPS state embedded into n equals 4 super young Mills as some 1/4 or 1/8 BPS background. So all loop protected correlator would produce an interesting 2- or 3-dimensional quantum field theory, asymptotically free with non-trivial spectrum of masses, and maybe it could be solvable by gravity dual approach. And at the same time, we could study in this way the BPS 1/4 BPS operators, the correlation functions of 1/4 and 1/8 BPS operator. This model, the principal chiral model, is integrable, and there are nice results in some old papers and some new papers of which we wrote with Evgeny Sobko and Kostya at large n. So it's essentially large n. It's a completely solvable model, one can say, at large n. If all these gauge gravity correspondences is true, then it opens a lot of opportunities. Okay, that's it. And now happy birthday, Joe. I presented here, so you probably guess who is my co-author here. That I thought it would be a spin chain here around, but my co-author insisted that it's kind of a crown of thorns instead of, which is sometimes true in our business, yes. Okay, happy birthday and thank you very much.
Володя. Thank you for the talk. Is it possible to also rewrite the functional integral of super young Mills as a Gaussian integral over complex matrices also in other dimensions? So for example, in 3 dimensions or not?
You mean ABGM or what? Or super young Mills, I mean, the logic is that it's of course an interacting theory, but on this class of operators, it becomes Gaussian. And then you can rearrange 6 matrices as 3 complex matrices, etc. But maybe
Thank you. Yeah, I'm ignorant to the topic, sir.
Okay.
So, okay, maybe I want to get rid of the screen. So, so going back to another slide. So I didn't understand something about in the rectangular giant graviton.
Ah, I see.
You had K and N, and
it's the previous slide. Yes.
So N, which N is this?
No, this is a rectangular Young tableau. Like.
Oh, but I know, but it looks like is this the same N as N in SUN or no?
Yes, of course.
Yeah, but then that's a trivial.
In UN.
Oh, it's UN.
In UN, yes, probably it's UN.
Oh, okay, so it's UN. Okay. Because I thought.
But one can probably it's make it shorter and compute also.
You can do it. Doesn't have to be all the way down.
Okay. Yeah, you can even build it out of a few such. I mean, you can build more and more rectangles, and in principle, there are generalizations of this formula.
I see. Okay.
Thank you for the nice talk. I have a question in the next slide, in the last slides, the one before the crazy picture. Yeah. Next one. When you talk about the Gucci Kawaii, so I thought that at least the not twisted one could be solved in the same method that you and Zeshuang have, like this plaquette, and then you do this like bootstrap numerically. Can you do the same for the twisted one, or there's no problem?
This is in the plans. If my collaborator and my former students, Zechorn Zhang, will be interested in it, which I try to convince him, then I think it's a very good example for doing it and really checking, because there you just solve loop equations which contain all phases of the theory. So you will really see whether there exists a physical phase.
Any more questions? So in some previous slides, where you discuss critical regime in the eigenvalue distributions.
It's, you mean, even the previous one. This one, yes?
Yes, so what does it mean? I think it's like fine-tuning the coupling T2 and T3. So it's like
yeah, you have essentially two couplings. Or for example, you can put T4 to 1 and consider the area of this object as a variable, the number of eigenvalues inside. Then you have, say, one coupling is T2. You can tune it in such a way that you have this criticality. And then it will be this generic one, 5/2. But then by other coupling, you can make it 7/3. You have, in this curve, you have singularities outside of the curve, which approach, when you change the parameters, approach the boundary. And once they hit the boundary, you have this kind of beak. Then if you change it further, you simply two singularity center hit at the same place, and then you have this next multi-critical points. There is still an issue, unclear issue, whether this is really describing the unitary critical points like Ising, or it's just these multi-critical points which I once introduced in the one matrix model. But I don't think any is any. I think this complex matrix model has all kinds of critical points.
Yeah,
PQ.
Yes, but from the point of view of any equals 4 superimage, you are looking at some very special type of operator, and you find some critical.
I define it by this potential, yes. in the exponent, but I can add more and more terms, and this is standard story. You add more and more powers to the potential, and you can tune more and more couplings to make it multi-critical.
So if there are no more questions, I suggest to thank Volodya again.
Thank you. So I have to conclude, I guess, or you conclude. I think.
I think we should thank Kostya, Maxim, and Anton for organizing this wonderful conference.
Absolutely.
Most thanks should go to Anton, who actually did all the work.
Yeah. Thank you.
We should thank the speakers for very inspiring talks. Also, I guess we should ask Joe for being here with us and for sharing his wisdom with us. And happy birthday, Joe.
So, okay, I was gonna, Arkady did the work for me, but I wanted to thank Kostya and Maxim and Anton for putting together this very memorable day for me. I'm honored to be here, and I'm very thankful that you all were able to come. And it was great seeing old friends again. And well, it's a thing here, and I'm happy to be here. So thank you very much. And one more thing. So Anton did, as Kostya said, did all the work. And Anton gave, as always, a beautiful talk. And I'm looking forward. He's going to take a break to come back to Sweden for a bit, but I'm very much looking forward to seeing his talks again in the future. So Anton, thank you very much.